those CMOS sensors, could they actually be repurposed to generate significant electricity? Like maybe even power your home? Sounds a bit like science fiction, right? Well, today we're taking a deep dive into exactly that idea.
Yeah, it's a fascinating concept. Our source for this is a really detailed analysis, part of a larger work called CMOS, From Imaging to Self-Powered Microsystems. And it specifically looks at repurposing imaging for energy. So our mission today, really, is to unpack the common ground between digital cameras and solar panels, explore where their designs totally diverge, which is, spoiler alert, quite a lot, and uncover the very specific kind of niche area where CMOS can actually be used for energy.
Okay, let's unpack this then. So at the most basic level, they both start with the same thing, right? Converting light into electricity, that's the bedrock.
That's exactly right. It all boils down to the photoelectric effect in semiconductors, usually silicon. So when a photon, a particle of light, hits the silicon, if it has enough energy more than silicon's bandgap energy, which is about 1.12 electron volts, it knocks an electron loose, creating what we call an electron-hole pair.
And silicon's good at this for visible light.
Yeah, it absorbs photons up to around 1100 nanometers. That covers all the visible light and even some near-infrared. Crucially, the number of these pairs generated is proportional to the light intensity and its wavelength. So that's how a CMOS sensor measures brightness for an image, and it's also how a solar cell generates an electrical current. Same basic phenomenon.
Okay, so you've got these electron-hole pairs. How do the systems actually grab that energy?
That's where the PN junction comes in. This is absolutely critical. It's where you have P-type silicon meeting N-type silicon, and right at that boundary, a depletion region forms. Inside this region, there's a natural built-in electric field. It points from the N side to the P side. No external power needed. It's just there.
Like a little internal slope.
Sort of, yeah, an electrical slope. And when an electron-hole pair gets created in or near this region, whisk, that field immediately separates them. It pushes the electron over to the N side and the hole over to the P side.
And that separation is key, stops them from just canceling each other out.
Exactly. It prevents recombination. So you get electrons building up on the N side, holes on the P side. This creates a voltage difference. N side becomes negative, P side positive. Now, if you connect an external wire, a circuit, that voltage drives a current. Electrons flow out, do work, and come back. As long as light keeps creating pairs, you get current. That's the fundamental principle for both.
It's amazing they share that core idea, but then, wow, they go in totally different directions. Let's talk CMOS image sensors first. These things are, they're just marvels of microengineering, right?
Yeah.
But designed purely for capturing an image, not making power.
That's the crucial distinction, absolutely. Modern CMOS sensors usually use something called a pinned photodiode, or PPD. It's engineered to be really low noise, very efficient at collecting charge for the image. But the defining feature of an active pixel sensor, an APS, is that every single tiny pixel has its own little support circuit built right in, usually 3 or 4 transistors.
Transistors in the pixel.
Right there. A reset transistor, a source follower amplifier, a row select switch. This in-pixel amplifier takes the tiny amount of charge collected by the photodiode and turns it into a much more robust voltage signal right at the source. That's vital for getting a good signal-to-noise ratio, especially when it's dim.
So it's all about measuring a tiny, precise packet of charge, not a continuous flow like a solar cell. How does the readout actually work then? How is it different?
Oh, completely different. A solar cell is all about continuous current output. A CMOS sensor works in cycles, frame by frame. First is integration. The photodiode just sits there collecting electrons, like a tiny bucket filling with charge. Then comes conversion and readout. The collected charge gets dumped onto a sensitive node, called the floating diffusion. The in-pixel amplifier measures the voltage on that node, which is proportional to the charge. Then these voltages are read out, usually row by row, across the sensor.
And converted to digital?
Exactly. On-chip, analog-to-digital converters, ADCs, turn that voltage into a digital number, a brightness value. But here's the kicker for energy. After readout, the reset transistor kicks in. It completely empties that charge bucket, clears everything out, ready for the next picture. From an energy point of view, that reset is just throwing away all the collected charge. Total waste.
Right. So if that's the process, what are the design priorities? What makes a good image sensor?
It's all about image fidelity. Top priorities are things like signal-to-noise ratio, SNR. You want the signal strong compared to any electronic noise. Dynamic range. Capturing details in really bright areas and really dark areas of the same scene. Spatial resolution, basically how many pixels you have and how small they are. And also quantum efficiency, QE.
QE. That sounds relevant.
It is, but maybe not how you think. QE is the probability that an incoming photon actually creates an electron that gets counted for the image. It's about detection sensitivity, not power output efficiency. A sensor can have great QE, but terrible power generation.
Got it. And what about those little lenses and the color filters on top of the pixels?
Yeah, those further highlight the imaging focus. Microlenses sit on top of each pixel. Why? Because a lot of the pixel's surface area is actually covered by that opaque circuitry we talked about, the metal wires, the transistors. This is called low geometric fill factor. The microlens acts like a funnel, gathering light from the whole pixel area and directing it onto the small light-sensitive photodiode part.
So boost the light hitting the active part.
Exactly. It improves the effective light collection for imaging, but it doesn't change the fact that much of the area isn't sensitive. Then you have the color filter array, CFA, usually a pattern of red, green, and blue filters. This lets the sensor capture color images. But think about it. Each pixel only sees one color. It's inherently blocking or reflecting at least 2/3 of the incoming light. For power generation, that's a massive loss right off the bat.
Wow, okay. So then we pivot to the solar cell. It's almost the polar opposite, isn't it? It seems like pure brute force simplicity geared towards one thing, maximizing power.
Absolutely. A photovoltaic cell is basically just one big PN junction spread over a large area. Everything about its design is optimized for grabbing photons and getting current out efficiently. You've got anti-reflection coatings on top to stop light bouncing off, surface texturing, often tiny pyramids etched into the silicon. This traps light, makes it bounce around inside for a better chance of being absorbed. On the front surface, you have a grid of very thin metal lines, the contacts to collect electrons, designed for good conduction but minimal shadowing. And the back is usually just a solid metal layer to collect the holes. No complex circuits inside the cell itself.
And the whole system around the cell is also geared for power, right?
Yep.
The inverters and stuff.
That's right. The cell itself produces direct current, DC. But your home appliances, the grid, they run on alternating current, AC. So you absolutely need an inverter. It takes the variable DC output from the panel and converts it into stable AC. And very often, inside that inverter, or sometimes as a separate unit, you have maximum power point tracking, MPPT.
MPPT, what's that doing?
It's constantly monitoring the voltage and current coming from the panel. The amount of power a solar panel can produce changes with sunlight intensity and temperature. There's a specific voltage and current combination, the maximum power point, where it generates the most watts. MPPT continuously adjusts the electrical load on the panel to make sure it's always operating right at that sweet spot, squeezing out every possible watt.
Makes sense. So the metrics for success must be totally different too. What defines a good solar cell?
Completely different priorities. For solar cells, the number one metric is power conversion efficiency, PCE. That's simply the ratio. How much electrical power comes out compared to the total sunlight power hitting the cell. Standard commercial silicon cells today, they're typically in the 20 to 25% range.
Okay, what else?
Then there's fill factor, FF. Now, this is an electrical metric, not geometric like in CMOS. It describes the squareness of the cell's current voltage, IV curve. A high fill factor, often over 80%, means the cell can deliver power efficiently near its maximum point with low internal resistance losses. And ultimately, the big driver, especially economically, is cost per watt. How much does it cost to manufacture per watt of peak power it can produce? And that cost has just plummeted, like over 99% since the 70s. It's made solar incredibly competitive.
And they scale up easily.
And massively scalable. A single cell only produces maybe a volt or two, a couple of watts. So you wire them together in series to boost the voltage and in parallel to boost the current. That makes a module or a panel, and you can connect panels together into huge arrays to generate kilowatts or even megawatts of power. That's a fundamental advantage for bulk power.
Okay, so we've seen the two paths diverge. Let's really hammer home why you can't just use one for the other's job. Despite that shared starting point, they really are products of totally opposing design needs.
Exactly. Let's look at the structure and materials. CMOS sensors use these complex, very shallow PN junctions. Things like N plus P substrate or P plus N weld substrate. They're meticulously engineered for ultra-low dark current leakage when there's no light, and for super-fast, complete transfer of that tiny charge packet to the nearby amplifier. They need incredibly pure, defect-free, single-crystal silicon wafers. The doping profiles are complex, non-uniform, designed for precise control of electrons.
Expensive stuff.
Very. Now compare that to a PV cell. It uses a single large area junction, but it's much deeper. It's designed to absorb photons and separate charges over a bigger volume, and they can use cheaper materials. Polycrystalline silicon is common, or even thin films like cadmium telluride or CIGS. Less pure, cheaper to make. The doping is simpler, too, aimed at creating a strong, uniform electric field across that deep junction and ensuring the electron-hole pairs live long enough to be collected.
And you mentioned fill factor meaning different things. That
Yeah.
seems crucial.
It's a huge difference, and the naming can be confusing. For CMOS, geometric fill factor is about physical area. What percentage of the pixel surface can actually detect light? And it's low, maybe 30 to 80% at best, because all that circuitry, the transistors, the wiring, is opaque. It blocks light. That non-sensitive area is probably the single biggest physical roadblock to using it for power. Remember, microlenses help imaging by focusing light onto the sensitive part, but they don't magically make the whole pixel sensitive. Energy hitting the circuits is just wasted as heat.
Okay, so that's the physical layout limit. What about the electrical fill factor in PV?
Right, for PV, electrical fill factor describes how efficiently the cell delivers the power it generates. It's related to internal resistance. But the physical design goal for a PV cell is to have a geometric fill factor near 100%. The only thing blocking light, ideally, is that very thin grid of metal contacts on top. Almost the entire surface is active.
And the QE versus PCE thing, let's clarify that again. High QE doesn't mean high power.
Not necessarily at all. QE, quantum efficiency, for CMOS is about detection. For every photon hitting the sensitive area, what's the chance it generates an electron that contributes to the image signal? High QE means a sensitive camera. PCE, power conversion efficiency for PV, is the bottom line for energy. Of all the light energy hitting the entire cell area, how much comes out as useful electrical power? A standard CMOS photodiode, even without the filters and circuitry losses, just isn't designed for high PCE. Its structure is wrong for efficient power extraction.
So what kind of PCE are we talking for a CMOS photodiode itself?
It's generally very low. Research prototypes using modified CMOS processes might report PCEs anywhere from, say, less than 5% up to maybe 10 or 12%. There are some specialized, highly optimized lab results claiming higher, even near 25%, but these often use non-standard processes or structures. Compare that to standard, mass-produced silicon solar cells readily available at 20-25% PCE. So yeah, to sum it up, CMOS is about micropixels, amps, SNR, resolution. PV is about large area, single junction, PCE, cost per watt. Fundamentally different beasts.
Okay, so given all that, trying to adapt CMOS sensors for like utility scale power generation, what are the biggest hurdles? It sounds like it just completely falls apart.
It really does collapse under scrutiny for bulk power. The inherent problems are just too large. First, those inherent inefficiencies we talked about. The low geometric fill factor is killer number one, too much dead area. Then the optical losses. Those filters block most light. Other layers in the chip stack absorb or reflect light before it even reaches the silicon. And third, parasitic power consumption. All that complex on-chip circuitry, the amplifiers, the logic, the ADCs it needs power to run. In an energy harvesting scenario, that circuitry becomes a load, potentially consuming more power than the photodiodes could ever generate.
And the whole way they operate, that cycle is wrong for power too.
Completely wrong. That integrate readout reset cycle is designed to measure discrete packets of charge for an image frame. It's not set up for continuous current. If you tried to modify it for continuous output, you'd essentially bypass the imaging electronics, so it wouldn't really be a CMOS imaging sensor anymore. Plus, studies show that running these sensors slowly, which you might think saves power, actually increases the energy cost per pixel. They're just inefficient for steady-state operation.
And heat. Power generation makes heat. Imaging sensors hate heat.
Exactly. Thermal constraints are another major conflict. Generating power inevitably produces waste heat. Higher temperatures reduce photovoltaic conversion efficiency, but higher temperatures also dramatically increase leakage currents and electronic noise in those sensitive CMOS circuits, degrading image quality. The two functions are basically thermally antagonistic. They work against each other.
And then there's just the sheer cost. The economics must be completely prohibitive.
Oh, the economics are probably the final nail in the coffin for bulk power. CMOS fabrication is incredibly complex. We're talking hundreds of process steps, nanoscale precision, multi-billion-dollar factories, fabs. Processing one 300-millimeter silicon wafer costs thousands of dollars. That cost is justified because you get billions of sophisticated transistors doing complex computations or imaging. PV manufacturing, on the other hand, is streamlined for cost-effectiveness over huge areas. Fewer steps, less precision needed. The cost per watt for solar panels is now well under $1. Trying to make solar panels using a CMO fab. The cost would be astronomical, orders of magnitude higher per watt, and the efficiency would be terrible. It makes absolutely no economic sense. CMOS value is complexity at the microscale. PV value is efficient area at low cost.
Okay, so powering your house with your old phone camera sensor. Definitely science fiction. Buddy T, Here's where it gets really interesting again. You said there's a niche. While bulk power is out, there's a microscale application where this CMO tech actually makes perfect sense.
This is the exciting part, yes. While CMOS is awful for bulk power, it's potentially brilliant for microscale energy harvesting. Think about the Internet of Things, wearables, implantable medical devices, billions of tiny sensors and processors. Powering them is a huge challenge. Batteries run out, need replacing or recharging. That's often impractical or impossible.
Right, you can't change the battery in a sensor embedded in a bridge
Right.
or easily in a medical implant.
Exactly. So energy harvesting, pulling tiny amounts of power from the environment, like ambient light, vibrations, heat, becomes really attractive. And this is where CMOS shines because of monolithic integration. You can use the standard, mature, cost-effective CMOS manufacturing process to build not just the sensor or the logic circuits, but also the tiny power source like photodiodes optimized for harvesting and the power management circuits, all on the same piece of silicon. That integration saves space, complexity, and cost compared to having separate chips for sensing, processing, and power.
So it's not about generating lots of power, but about generating just enough power, right where it's needed to make the chip self-sufficient.
Precisely. Make the chip autonomous. Cut the battery cord. Research is exploring several cool ideas here. Dual-mode pixels. Pixels that can electronically switch. Sometimes they capture an image, sometimes they harvest energy. Simultaneous harvesting and imaging. Clever structures like stacking two photodiodes vertically. Top one images, bottom one harvests, maybe different wavelengths of light. Also asynchronous or event-driven designs. Imagine pixels that only wake up and use power when they detect a change. When they're idle, they could switch to harvesting mode to help power the system.
And how are they overcoming that low fill factor problem within the pixel for harvesting?
They're designing specialized harvesting structures within the CMOS process. For instance, layouts like the isolated PUL energy harvesting and imaging EHI pixel. These dedicate more area specifically to the harvesting photodiode, pushing its geometric fill factor up, maybe even to 90% or more for the harvesting part. But the voltage from one tiny photodiode is still really low, maybe only 0.3 to 0.5 volts, too low for most circuits.
So you need to boost it up.
Yes. So critical components are integrated on-chip power management units, PMUs. These include tiny DC boost converters, often using charge pump circuits to step up that low voltage to something usable, like over 1 volt. And they're even integrating miniature MPPT circuits right on the chip to maximize the power gathered from varying light conditions. It's incredibly sophisticated micropower engineering.
Wow, that is amazing. How much power are we talking? Is it actually enough?
It's tiny amounts, but the circuits they're powering are also designed to be ultra-low power. It's about achieving a net positive energy balance. We're seeing reports like a 96 by 96 pixel array generating up to 30 microwatts. And if the imaging part only consumes, say, 6.5 microwatts, then the chip can run autonomously, maybe on a duty cycle, powered just by ambient light. Another example showed a sensor becoming power positive, generating more than it consumes in light levels above 50 kulux, which is like a bright overcast day.
So it's feasible in the right conditions.
Yeah.
And the efficiency.
The efficiencies are improving. Those on-chip charge pumps can reach maybe 60–70% electrical conversion efficiency. The overall system-level PCE, light in to usable logic power out, is still modest, maybe around 10% reported in some integrated systems. But the photodiode part itself, optimized within a standard CMOS process, can achieve PCEs of maybe 12.5%. The key isn't matching solar panel efficiency. It's achieving energy autonomy on the chip itself. It's a totally different game.
Okay, so let's wrap this up. What's the big takeaway for you listening to this? It seems crystal clear. CMOS image sensors and PV solar cells started from the same place, but they're worlds apart now. Using your camera sensor as a solar panel, just not going to happen.
Absolutely not for bulk power. But the really exciting story is that microscale, on-chip energy harvesting, using those same CMOS processes to integrate the power source right alongside the circuits it powers, that's a potential game changer for tiny autonomous electronics. Looking forward, the research is really pushing on system co-design, optimizing the harvester, the power management, and the functional circuit together to minimize power needs and maximize supply.
And improving the materials or processes.
Definitely. Can we tweak standard CMOS fabrication to make the photodiodes better at harvesting, maybe absorbing more infrared light without messing up the logic transistors? Or exploring advanced 3D architectures, maybe stack a layer optimized purely for harvesting on top of the standard logic chip that could offer the best of both worlds?
And maybe combining light with other energy sources.
Yeah, hybrid harvesting systems look very promising. Imagine a chip that harvests light when available, but also scavenges energy from vibrations using tiny piezoelectric elements, or from heat using thermoelectric generators, all integrated together. That makes the device much more robust.
So here's the final thought to leave you with. Imagine that future Internet of Things. Huge networks of smart, maybe even invisible, sensors everywhere, monitoring our environment, our buildings, our health. For that vision to work, these devices need to last for years without anyone touching them. So while that CMOS sensor in your phone won't replace a solar farm, the underlying technology adapted for on-chip energy harvesting could be absolutely vital. It's about finally cutting that last tether for microelectronics, the battery.